I am going to be talking about graph neural network interpretability, kind of in HEP and kind of not, as we'll see. Kind of the motivation for this talk is I feel like physics and machine learning are generally concerned with kind of the same question, at least how we use machine learning, which is that, and sorry, let me move the Zoom thing. Here right now. Great, so we want to characterize the true probability distributions of nature. And if we're doing this with a machine learning model, like how do we understand which of those models are most accurate and most predictive? And how do we use such a model to do science? So I've been, talking to various people here about this kind of question of like, what does it mean to do machine learning or to do science with machine learning in the first place? If we can build a model that is, predictive, but we can't understand it, like, does that still count as doing science? I think there's a lot of motivation for asking these interpretability questions when we're trying to use machine learning models to assist us in doing science. And I think for GNNs and geometric deep learning, it's particularly interesting to ask these questions because just by nature of the kind of algorithms we're using, we're bringing in a lot of inductive biases already. We have these kind of geometric inductive biases. We can do things like enforce equivariance very easily. And so then in some sense, these interpretability questions become perhaps even more interesting. So Daniel mentioned this in the talk he just gave. If these heterogeneous GNNs work better than homogeneous GNNs, where is that improvement coming from? Like, is it that we're modeling different detector materials better? And similarly, we asked a related question in a paper that we did about enforcing equivariance, where we found that, allowing some non-equivariant information into your GNN, at least for this task we looked at, worked better. So like, it really motivates this question of, well, why is any of this happening? Like, what does it mean about physics that we're seeing these behaviors in our models? So that's my spiel for why I think this talk is interesting and important. So a quick outline, I'm gonna first go through 3 different examples of interpretability techniques that we've applied in HEP. 2 of them use GNNs explicitly. 1 of them does not use GNNs, but I'll make some, comments about how this could be extended to GNNs. And then I'll also show some examples of GNN focused interpretability techniques that have been developed from, I say industry here, but by that I mean broader machine learning outside of physics. And then some prompts for discussion that I think we should talk about. So first, kind of starting with what I feel like is the first step that people usually do for doing some kind of interpretability or explainability, which is looking at things like feature importance and relevance propagation. So this is probably the thing that's been done most in, I would say, HEP efforts around interpretability. So here I'm showing first a CNN image-based example because this has a bit more work than in the GNN applications. But so here, we're doing this jet image-based jet tagging approach with CNNs, and you can then kind of look at the different factors of the CNN architecture itself to try to do some kind of post hoc interpretability. So for instance, you can look at the correlation of the network output with standard physics features to kind of say, is it learning things that we expect to be important about jets? You can look at, average images with highest activations for the last hidden layer and kind of look at the differences between, I forget exactly what I think they're doing, QCD versus top jet tagging in this paper. But so you can look at like the average images that, give your network a really high activation for the top tagging label versus the QCD background label, and we see, qualitative things like we have this second core in the top jets that we don't have in the QCD jets. You can look at things like the learned filters that your CNN is learning and kind of see where it's attributing attention in some sense in your network. And again, like we're kind of seeing the same qualitative things with all of these different approaches, that the presence of a second core matters. That maps onto what we know about physics. You can do more specific things like look at only a certain type of jet or something. But the point here is that it's not very quantitative. It's more of a like qualitative kind of attention mapping interpretation. And you can do things to make it like a little more precise. So in this paper, they augmented the CNN with some physics motivated variables after you do the initial convolutions. And then you can use layer-wise propagation, which basically starts with your output feature nodes and propagates relevancy values back through the network to see more specifically, instead of just these visualizations, like where attention is being focused in your network. So you can see like how important different features are to the final output of your network. So basically you map back through your network to your original input features and you get some sense of importance. And this is helpful in that you can show really that the network is actually learning some expected physical relationships. You can look at like relevancy heat maps between different features and see that it behaves the way we expect physically. But what they found, at least in this paper, is that like the image representations that you can concatenate with the expert features at the end are still by far like the most important thing that the network is leveraging for its decisions. So we're not really still learning anything about what the image representations are doing. So it's a little bit more specific, but still like not super helpful in understanding these hidden representations. But this same kind of technique has been applied to GNNs in this really interesting paper that looks at that machine learning particle flow algorithm that Javier talked about this morning and various people have talked about, where you're using graphs based on reconstructed detector elements like tracks or clusters. And there are different features to do some node classification prediction, which is typically particle ID, but can also be things like particle energy and charge. And so you can modify this layer-wise propagation formula to accommodate the aggregation step. That basically is kind of the difference between graph neural networks and standard neural networks. So you just modify this relevance propagation formula to distribute like the aggregated neighborhood information to the unaggregated nodes in the previous layer of your graph neural network. And then you can like construct relevancy score tensors for each node in your graph that describes how the different features of the neighborhood nodes contribute to the decision on a specific node. So instead of getting this global behavior for your network, you kind of look at how it contributes to individual nodes. So you can also get a sense of like how important each feature is from each of its different neighbors. Like maybe we're carrying the network really heavily weights charge, but only from the nearest neighbor in your graph, and charge from the farther away graph features, or sorry, graph elements don't matter. So then you can average this order over events again to kind of get a sense of like what is your network learning, what is it weighting, and we see, or they see in this paper that for distinguishing charged versus neutral hadrons, when you're looking at charged hadrons, it uses more information from the surrounding nodes in its decision, particularly it uses more information about charge when it's giving a node an end charged hadron classification label versus a neutral hadron classification label. So again, this is like good. It seems to be learning, things that we know should be true in physics. It's not doing something, totally out of the ordinary. But again, this kind of approach, I would say, doesn't like fully characterize a machine learning decision. It just gives us some tools to maybe say is doing something that we expect in addition to like the other things that we don't understand yet. So, which is, kind of what I'm summarizing here. We can sort of check if a model is learning about physics features that we know, but we don't really, this doesn't give us a way to interpret what else it's learning. There's no clear way to match like those image relevance maps that I showed at the beginning to actual mathematical or physical information. Also a big critique that people have of things like salience mapping and relevance propagation is that there's not necessarily a way to say that this is due to like true generalizable physics versus just some artifact of the specific data set that you're looking at or the specific network that you've developed. And they also don't give us like performance on edge cases or difficult noisy samples or things like that. So it's helpful, but like not the full answer, I guess is the takeaway. So there has been some other interesting work in ways that we can perhaps get a little bit more mathematical about our interpretation tools. So again, I'm talking, this work is on CNNs and not GNNs, but I'll show in a couple of slides some ways that you could generalize this to GNNs. But so basically here they're trying to construct what is the learned information that a CNN is learning. So you train it again on jet images, and then you use that kind of low-level classifier to guide the construction of a classifier that's based on inherently interpretable physical features. So here they use average decision ordering to maximize the similarity between the decision boundaries of two models, where here your interpretable model would be something like a decision tree on high level features, so you can directly see like what information the model is leveraging. So they iteratively select these high level features from some subset or from some feature set that they've defined and maximize the average decision ordering between that and the low level classifier. And you can make this better with a kind of boosting technique where like at each step of your optimization, you separate out the samples where the low level and high level classifier disagree, and you can upweight those, and then that tries to push your high level classifier to be better. And so they demonstrated first that for this jet tagging CNN, the bulk of its power can be captured by 6 jet features that we already know about, which is already nice again to see that like the CNN is learning information that we know should be important. But what I think is a little bit more interesting is that in some cases you can kind of define a basis space that covers a very broad range of physically interpretable information. So instead of just using the jet features that we typically use, you can use something like energy flow polynomials, which are a theoretically infinite set of jet descriptors that are basically different kinds of functions that use as features the momentum fraction of color inverse cells and the distance or the pairwise angular distance between those cells. And so you can go to like higher and higher level orders of these energy flow polynomials theoretically forever, although like probably they become less interesting after a while. But so the interesting thing you can do here is you can take a subspace of samples where that 6 feature I think neural network is wrong here, but where that 6 feature interpretable model didn't match the CNN performance, and then you can use this energy flow polynomial basis as a space to do another decision ordering search. And this helps identify energy flow polynomials that help specifically on edge cases that the CNN was doing better on than traditional jet classification techniques that we use. So this is really nice. It helps us identify some of that information that the CNN is learning that we have not thought to put into jet taggers before, particularly like some of the EFPs that the network that seem to describe the network decision are very different than what we typically use in a jet classifier. So this is a very nice technique. The caveat, which I say in a couple of slides, is that like you often don't have a nice basis like this to describe what a network is doing. So this is cool for jet tagging, but we don't have it for every kind of physics task. There's also not any kind of guarantee that this parameterizes the whole space of what a CNN or a GNN could learn. So maybe we get farther, but I would say it's still probably not the whole answer. So since this is a GNN workshop, I'll mention how you could extend this similar technique to GNN. So people typically call this local black box approximation on GNNs, and you're doing the same thing here, except you're, instead of trying to learn a global approximator, people typically focus on learning an interpretable model locally in some subgraph of the node that you're like trying to generate an explanation for. So there's a nice paper that does this with like a lasso-based regularization to do that feature selection to approximate the GNN decision locally in an NHOP node neighborhood. And you can look at different neighborhood definitions. You can look at like different distances that you're considering the decision to be relevant for. But the idea is that similarly to doing that decision ordering search, you use this lasso loss with some predetermined set of interpretable features that you think are probably going to be interesting, and you try to mimic the GNN decision boundary in a local neighborhood. And they've demonstrated some nice like guarantees with this approach that it's robust to noise and to correlated features. But I would say the big gap here is like we still don't know how you define like what neighborhood is important to a decision. So you can look at different definitions, but there's no like there's no recipe for saying what neighborhood is going to be important. And if you find like a neighborhood definition that works well, to me that opens another interpretability question. Like, what does it mean that this is the neighborhood that's relevant to a decision? How do we interpret that? But anyways, pretty nice technique. So again, I've said some of these things already, but this method gives us, a specific quantification of what the network is learning, at least up to the level that we can approximate the non-interpretable decision with our interpretable model. We ensure that this learned information is like not a statistical artifact because we're mapping it back to some generalizable space of features. However, like I said, we don't always have a nice space of features to search over is a big problem here. But also there's some criticism of doing kind of saliency mapping and this kind of like interpretation of your local decision on graph neural networks in general, because of like the discrete and sparse input structures that we have in graphs with the adjacency matrix. There's some critiques that like maybe salient, like this kind of interpretability shouldn't even be done on graphs in the first place. So, again, not a perfect solution. Then the final example I'll talk about that I've seen people looking at in physics is symbolic regression. So this is where you try to find, and instead of an interpretable machine learning model, you try to find an analytical equation that mimics the prediction of some non-interpretable machine learning model. And there are different ways that people, have demonstrated that you can reduce the function space that you search over to make this a tractable problem. But typically it's done with some kind of genetic algorithm where you recursively build up a function from some basis space of input variables, mathematical operators, and constants. And basically you try to minimize, again, the error between your analytic function and your machine learning model prediction. And you can do things like enforce penalizations for complexity. So you try to generate a simple analytic representation that isn't like overfit to the specific machine learning model that you're looking at. All these different things. So there's a really nice example and these are slides that I took from another talk. And the paper is really great. I think their explanation is really great, which is why I'm showing it here. So this is an application of symbolic regression to GNNs, where the input to the graph is the position of different celestial bodies. You have pairwise distances as like the edge relationships between your graph nodes, and then the GNN tries to guess a mass for each body, and then it also guesses a force as a function of as some learned function of the pairwise distances and the guessed mass, the guessed node value. And then you can then like enforce some physics inductive bias on this network by plugging that force prediction into Newton's law of motion to get accelerations, and then do like a timewise step propagation using that acceleration to get new positions of the bodies in your graph. And then what you actually compare to train the network is the difference between the predicted and true acceleration. So you're kind of already enforcing physics constraints into the construction of your network, which is really nice. And this works, their GNN works pretty well for both the mass prediction and the like trajectory prediction using this predicted acceleration to do time step propagation. But what is interesting from the interpretability side is you can then apply symbolic regression to the GNN messages, these predicted forces, with a constraint where they balance the trade-off between equation accuracy and equation complexity. And you get from the symbolic regression package this candidate list of equations. And we see that the highest scoring one is in fact like the gravitational equation of motion for a two-body system. So it's very nice that we're able, in this kind of simplified constraint example, we're able to get back the physics equation that we know is true. And then you can actually take that equation back and improve your network. So instead of doing a random force guess or a learned force guess, you can use this equation to do the force calculation and further improve the accuracy of your model. And they've demonstrated that this approach can work in more complex systems as well. Like there's work in the paper that I cited of using this to learn models of like dark matter halos and more complex things than just extracting the equation of motion. But I think symbolic regression is a really interesting and promising interpretability technique. Because you get something that's generalizable by construction, right? Like you're getting an analytic equation that then you can use to make predictions, and we inherently understand that. So you can kind of use machine learning development as like a guided equation search, where our final thing we're going to use is the equation we get out, rather than the model itself that maybe has some problems that we don't totally understand because it's not interpretable. Maybe it has different kinds of artifacts like baked into the construction. If you instead take the learned equation that approximates your decision, you get around some of those kind of things. But of course, like all the other examples I showed, this is not perfect. You don't know which equation to pick. Like if you just pick the one with the smallest error, it might not necessarily be the true description of nature. Simplicity of an equation as a decision factor is a big assumption that we make all the time in physics, but like is not guaranteed to be true, even though like it works well in a lot of cases. Deciding what constraints and priors to incorporate into your model. So like the one I showed here, you have your GNN priors, they also have the like Newton's law as a prior. So that will impact the class of equations that you get out, right? So if any of the constraints you put in are wrong, then the equation that you get out from symbolic regression has that wrong assumption baked in. So, you know, again, not a perfect system. And then I would say the biggest concern with this approach is like, if you have some kind of uncertainty or mismodeling in your data or reconstruction software that you're using to get the data to train your network in the first place, obviously the symbolic regression equation that you get out is going to be a model of your inaccurate training data and not necessarily a model of nature, which is the, you know, the big problem with using machine learning for any of this in the first place, I guess. And then quickly, I'll show some other GNN interpretability methods that are getting a lot of attention in the broader machine learning space. So perturbation-based explanations are, I'd say, maybe the most popular like GNN explainability technique right now. So the idea is that you try to identify maximally relevant subgraphs that contribute to the decision of a particular node. So there's two frameworks that are fairly well adopted. So first, GNN explainer tries to learn a graph mask that basically picks out what are the really relevant nodes and edges to the decision of a particular node you're looking at, and it does this by maximizing the change in the prediction on the node you're explaining by applying this mask. So it tries to find the mask that maximizes the change. And you can use the same approach to learn a feature mask, which maybe kind of relates to the heterogeneous GNN thing we were just talking about, where you can have a learned set of features for different nodes. And this allows qualitatively like edge and node-based counterfactuals. So you can say that like if the subgraph that like maximally changes the decision of a particular node is created by getting rid of a certain edge, then that tells us that edge is super important, and you know, maybe that's something useful. It's a little hand wavy in my opinion. And then CF GNN explainer is focused specifically on counterfactuals, and it uses edge deletion to identify the minimum prediction altering subgraph. So this has a guarantee of like, it's the smallest change you can make to your graph such that the decision of the particular node changes. So it's interesting in that like it has that guarantee, and so you get actual specific counterfactual explanations where like you can specifically say if this thing changes, that is like the least change that we need to alter a decision. Then there's some work trying to map some of the explainability techniques from CNNs that I showed like back at the beginning, where we have these visualizations, to GNNs by kind of creating the concept of filters in GNNs that then you can visualize. So here they learnable hidden subgraphs. And then you take the kernel function of those learnable hidden subgraphs with the actual neighborhood of the node and the graph you've specified during training. And that kernel result is what you use to do the node update. Like that becomes the message that you use to update your node. So this is not just an interpretability method, it's like an alternative way of training GNNs that maybe gives you some interpretability soft guarantees. So like what's interesting from the interpretability side here is that you can then visualize those graph filters that it learns and the application of those filters to the input graph to kind of see like what is important the decisions. And what's interesting here is like you get a sense of what's important across the whole data set that you're looking at rather than to a specific graph that you're trying to explain. So you can kind of get a sense of what structure is important to decision making overall instead of just in one specific case. But again, it's very hand wavy, the same way that visualizing CNN filters is hand wavy. Like you get an idea, but it's not mapped to a mathematical language. And then finally, there's a lot of different approaches to doing disentangled representation learning on graphs, which is disentangled representation learning is the idea that you're trying to separate the input information to some low-level classifier into features in a latent space such that the latent space of your features can be mapped back to some human interpretable values. And this is quite hard to do in a lot of cases. There's no like, specified recipe for doing this successfully in every case. But it's a really active area of research, and there's some methods proposed specifically for GNNs that have demonstrated at least some usability in different application areas. Typically, people look at them for like molecule graphs. I haven't seen really many examples in particle physics, but I would say just look at the papers here instead of my very short attempted summaries. But there's different ways you can use like different kinds of graph network construction or adding like learning tasks to your GNN that ask it to do disentangled representation learning while it's training for whatever downstream decision you're trying to make. And there's different ways people have proposed to do this that may not be successful if we try to apply them to HEP, but I don't think anyone's looked at it yet, so it seems interesting. So this is my introduction to interpretability for GNNs, interpretability and HEP, these different ideas, and so I'll end with some discussion prompts. So going back to what I said at the beginning, is interpretation necessary? Like if we can demonstrate that a model's decision is robust and accurate, do we need to understand it? How precise does interpretability need to be? Like, do we need to map back into a mathematical language that we can interpret in terms of fundamental physics values? Is it enough to do these softer interpretability, like saliency mapping techniques? I think this question is really interesting. So a lot of like GNN explainability focuses on counterfactual explanations because that's really relevant in a lot of applications of machine learning. Like, so if you use a knowledge graph to make a prediction about like someone's recidivism rate based on their social connections, you really want to be able to explain like, how would we have gotten a different decision for this particular person? So a lot of explainability techniques that are developed are focused on that. And I don't know that that's necessarily a question that's relevant to physics interpretations. Like, do we care about specific decisions and how those decisions would change, or do we care about what generalized information the network is learning? How do we encourage people to look at these problems? Like, I think colloquially, people seem to care, like we want to trust the machine learning models that we use, but then I don't see too much like actual research effort happening here. And then, yeah, so these are just all things that I think about. I'm just listing them off. For GNNs, specifically, there's been some rhetoric around like, can we call attention an attention mechanism and interpretability technique, where we can say, mathematically, we're prioritizing this kind of information. Is that interpretation? Also, we make a lot of claims that if you do equivariance enforcement, that somehow gives you more interpretability, but like, does it really? Haven't been convinced yet. And then this last question is like this morning after making this talk, I woke up to an email that was like, is interpretability impossible? Here's a paper that recently came out that maybe claims that it is impossible to balance robustness and interpretability. So is this even useful? I'm not sure. So thank you.
You mean is it useful? The idea is to feed all the LHC data in a massive big network, and then we have a like a function generator that spits at the end out a new Lagrangian with sectors which we just need to reinterpret as new physics. Fantastic. You showed it all.
Yeah, right. Totally. Science is solved now. Questions, thoughts?
So symbolic regression, which seems of the things you said, it seems possibly the most, and as a physicist, is possibly the most interesting, right? Trying to see if you can find some law, whether you knew them or not. But what I don't understand is, I remember seeing a graph like the one here in your slides with the cosine and the polynomials in talks from Kyle about probabilistic programming. And the question is there, what's the base? What do you decide are the x's and the cosines? What are the pieces? I mean, how did they do it in the astrophysics case? How did they decide to, because they knew already the answer, right?
Yeah, I mean, typically you just have an open space of like mathematical functions. So you include trigonometric functions, you include like, addition, subtraction, division, all of these things. Like you just define an open basis space and let it search over that. So perhaps there is tuning you can do there. Like if we, I don't know. This is like the question I feel like with doing all of this is we definitely know some things about physics, obviously, right? We've been doing this, for hundreds of years. And how do we put that into a machine learning model? There's no like recipe or prescription for how to do that right now. So maybe you can constrain the space of functions that your symbolic regression is searching over. Does that actually help, or are we enforcing like a bias in how we model physics in the first place? Like, I don't know.
No, for example, for tracking, it would be good to see that, the propagation of a particle in a magnetic field. I mean, we know that it's there, and that's prior. That's a strong prior. I mean, if the magnetic field equations don't work, we have a bigger problem, right? So I think it would be good to see that somewhere in the network.
Yeah, but as far as I know, no one has looked at symbolic regression for tracking.
So you put it basically as a similar as to the example the astrophysics group did, and see whether you probably would do a more simplified data set as the one we had as a start with to do a feasibility, as the one we had done for the very first kickoff TrackML hackathon with like really helical simulation, 3D points, a bit of noise, and then see whether in a very similar way with this symbolic regression, whether you can extract the Lorentz force or helical equations out of it.
Yeah, no, that is probably a useful thing to do.
Yeah.
So in the astrophysics paper, when they find the 1/1 cube or whatever it is, did they then you said they used it? So did they change their models to incorporate that explicitly in the model?
Yeah. So what they do is once you've learned this first version of a GNN that just has some unspecified function to do the force guess. Once you've learned like a good symbolic regression candidate, which in this case is the right answer, then instead of using the learned function, you can use the symbolic regression analytic approximator to do the force prediction. And, unsurprisingly, because it's the right answer of gravity, like it makes the model work better. To do that, you get a better mass prediction. I don't actually have their plot, but there's a version of this plot where once you've incorporated the actual force equation, your GNN learns much better mass guesses because, of course, like you're
So
telling it how
it's-
gravity works.
But there is no new physics in tracking, right? I mean, we know the physics.
Right. So I do think it's like very parallel to this example. Yeah.
So that's why we could repeat this study and see whether this is a general way. The idea of the hope of course, if you develop an understanding how this works, that you could practically capture terms in an underlying law that you then start learning. Yeah. Well, would be surprising for you would probably could take our thought experiment of learning the propagation. I'm pretty sure if this works out, you should be able to learn that if you did the exact same thing with a pure electron sample, that there is a component you haven't described in your first one, which is the Bremsstrahlung through material or something, like you could start trying to see whether this actually starts learning more than your line propagation.
And then you end up with the 1 gigabyte model, which inside has the propagator and longitude and everything.
Right. Yeah. I'm not saying. I'm not saying you.
No, but it would be good. And I mean, I don't think interpretability is necessarily a way to get better results. It's a way to get people kind of a little bit more
This is the point.
comfortable with your results.
I think that's really
Yeah.
that would be the kind of the academic or educational aspect of saying it's not just fiddling on some parameters until things work, right?
Can Room people actually ask some question?
Yes. Questions on Zoom. Sorry.
Yeah, Samantha, it's a really inspiring talk. So regarding you have like a slides like a GNN explainer, trying to using subgraph to determine a particular like for example classification. So if I try to put this like a Higgs boson event, I trying to find lots of background lots of background tracks, lots of actually interesting track. So that possible you can use this method to see, oh, this is a interesting tracks, really give the high score to the particular classification. Say this is an interesting event. Do you think that this can accomplish that type of goal? And then give the physicist, okay, this is the tracks really actually give me the determination.
Yeah, I mean, so I haven't seen a GNN that does that kind of classification specifically, but I think like theoretically you could do it with this kind of particle flow approach where you have instead of identifying jets or something, you could potentially set it up such that you're identifying event types, right? Like the presence of a Higgs boson or not. I think there's maybe some steps to get to that kind of GNN existing, but if that kind of GNN exists, then I think, yeah, absolutely, you could use something like a GNN explainer to look at like what then tracks or different detector components are useful for doing that identification. But I haven't seen a GNN like this yet.
Okay.
On that point, this is Daniel. Could you then design your detector to exploit those interesting channels? Could you? No, good one. This would be an alternative to the kind of mode approach, right? Where you have a totally differentiable detector. Instead, you go the other way and you say like, well, can I interpret the model? Yeah, in some way. I'm not sure exactly what the question is, but
Yeah, I mean, this is definitely, I would say this fits in the kind of like automating science space that like people are interested in the intersection of machine learning and physics, we're like, yeah, could we design a better detector that helps us make the kind of decisions that we're interested in making? I think like that's not outside of the realm of possibilities. It's I I think in some sense it comes down to what do you value, right? Like if we're saying we're able to make decisions and predictions, and this type of information seems relevant, so we're gonna prioritize that, getting that type of information. The other people might be like, no, we know this about physics. We should not change how we design physics detectors based on something we've learned from machine learning, even if maybe it could work well, right? So I think it's an interesting direction, yeah, but will it happen?
Does that not stumble in the same problem Andy talked about? We talked about this, that you're gonna run jams at every step of the training.
Sorry, what
I mean, if you're doing detector design.
oh,
You,
yeah,
But I guess, sorry, just to, maybe I'm thinking
What is
this
your-
is
what
a
is
kind
your
of
training
complementary
pipeline?
thing,
Yeah.
right? That would be like you're optimizing your whole pipeline towards some detector design.
yeah,
And I guess this is like, given a detector, what is the most important element of it by some interpretability? And then change the detector, but you don't have to, yeah, I guess you still have to run down every time. But maybe this guides your search. It's not like
yeah.
as
Yeah.
complicated as
So-
an optimization.
So the way what I showed, the way that DeepMind have overcome this problem that overcome is a big leap, have facilitated this sort of differentiable approach is that they built the simulator themselves is part of the graph.
it's like the wrapped
Yeah,
design.
while at least at our current stage for really a detector design, yeah, type of thing, we have a hard time doing anything else than some sort of at least approximate Monte Carlo simulation.
Yeah, or a generative thing that maybe we'll hear about this afternoon. I don't know.
Yeah, or generative thing.